Okay, hi, a very good day to everyone. Today we are going to look at the first part of application of graphs, which we are looking for the rate of change of a certain water depth or the height. So for this case, we are very interested to see, like, when we fill in water in a certain container, how would the depth change? And we're going to use this concept, right, actually to link this to other aspects of the graph. Alright, so the water depth graph is just a context for us, so that we can actually apply this into other form of graphs. For example, we can apply this into speed time graph, we can apply this to distance time graph, or maybe other kind of graphs. Right, so this lesson would be a very important lesson for you to really see how do we draw graphs and what do the shape of the graphs tell us, right? And specifically in this case, right, what does the gradient of that graph tell us? Okay, so the concept here that we are going to look at is the concept of gradient. Okay, so the concept of gradient, the concept of gradient over here, because gradient is actually what we call the rate of change, right? So the gradient is rate of change over of y against x. All right, so I'm going to put here rate of change. Okay, rate of change. Okay, so over here, so the thing to grasp with the things to grasp with is if the gradient increases, right? If the gradient increases, then the rate of change, right? The rate of change of your quantity is going to increase as well. So what does this mean is the change is going to be faster. It's going to be happening a lot faster in terms of the change. Okay, so where do we see the application in this? So the gradient is actually your change in the y value divided by the change in the x value. y2 minus y1, x2 minus x1. Change in y over change in x. So let me write that up in English so that you can really see. Right, change in y over change in x. Right, and in the same way, so this is actually the rate of change of y per unit of x. Right, so when we apply this, some of the applications would be things like speed, right? Is actually the change in distance over the change in time, right? And some of you have learned actually in physics, your acceleration, right? Your acceleration is actually the change in your speed over the change in time, the rate of change of speed, whereas the speed is the rate of change of distance, right? So these are some examples of gradient being rates of change, right? So today we're going to look at this set of rates of change in general first, before we move on to 5.5B and 5.5C, where we talk about distance time graph and the speed time graph specifically. Okay, so for this one over here, right? So the first idea over here is that, let's say if we have a horizontal graph, what does this mean? The gradient is 0, right? If the gradient is 0, the rate of change is going to be 0 as well. So over here, the rate of change is going to be equals to 0, like that. Okay, now let's take a look at the second kind of graph over here. So let's say if the graph is slanting upwards like this, but still in a straight line. Now over here, we can say that the gradient is actually a positive gradient, right? The gradient is positive gradient. In other words, the gradient is more than 0. So what, and this is actually, and then the thing is, does the gradient change or not? The gradient is actually a fixed gradient, because for a straight line, the gradient is always the same. So for this one, the gradient is positive and it is constant. Okay, constant. So means that this one over here, the rate of change, right? The rate is going to be a constant rate, right? Constant rate, and it's actually a constant positive rate, like that. Okay, now let's give another example over here. So let's say if you have another straight line going downwards, over here the gradient is going to be negative. In other words, in mathematical terms, the gradient is less than 0. And this is a straight line, so straight line has a constant gradient or a fixed gradient. So this gradient is constant as well. So because the gradient is constant, you replace the word gradient with rate. So over here, the rate of change is also constant, right? So it will be a constant negative rate. Okay, so what you need to do is just to change the word gradient to rate. That's all. Okay, so with this over here, let's take a look at the next two wilder examples. So I'm going to give you a curve like this. Okay, this doesn't do this justice. Okay, let's do it like this. Okay, so let's say if we have a graph like this, and at the same time we have another graph like that. Oh man, come on, give me my curve. Alright, so this one over here, another graph like that. Okay, so with this, let us take a look at two and how do we find the gradient of a curve again? We need to draw the tangent. Okay, so the first point over here, let me draw a tangent over here in the beginning, right? And let me draw another tangent at the end over here. Alright, so I think this is roughly balanced, and I'm just going to move this a little bit over here, I guess. This looks rather balanced. Okay, just an approximation, yeah. Okay, so let's take a look at the one over here. Now, this gradient versus this gradient. So the gradient at the beginning over here, alright? So this gradient over here is less steep. This gradient over here is steeper, alright? So let me put down in words over here. This is less steep. This is steeper, right? So what can you tell me about the gradient? Over here, the gradient is increasing. Okay, and because the gradient is increasing, right, you can actually say that the rate of change is increasing, right? Or the rate of change increases as well. Okay, so the gradient increase, the rate of change increase. So means that it's going to be faster, right? The rate of change is going to be faster, right? So it means that it's going to go faster. Okay, in the same way over here, let us draw two tangents for this graph. Ooh, okay, challenging. Okay, another one maybe over here. Okay, so let's say if you have two gradients over here, right? The first one is definitely steeper. The next one over here is definitely less steep. So what can you tell me about the gradient? The gradient from steeper to less steep. So this means that the gradient is decreasing. So when the gradient is decreasing, okay, let me write in red so that you can see the contrast, right? So the gradient is decreasing, right? So this means that the rate of change, right, is also decreasing. Okay, so what this means is actually it will go a bit slower, right? The change is going to happen a bit slower over here. Okay, so one more time, the concept that we need to learn here is that the tangent will give us the gradient for a curve, alright? The tangent will give us a gradient for a curve, and the gradient will actually tell us the rate of change. Alright, so the first two cases over here are pretty much straightforward, where you get your constant gradients or your zero gradient, which gives you the constant or the zero rates. But over here, this is what we need to make use of, right? So less steep and steeper. So like the steepness of the gradient will tell us at which part is going to be faster, at which part is going to be slower. Alright, so with this in mind, let us turn to the next page to look at this depth time graph over here. Alright, so we have a container being filled with water at a constant rate from a tap. So imagine the tap water just flows in like this, and at time t seconds after the tap is turned on, the height of the water is h. So initially it is empty and it just fills up again. So over here, if the container is a cylinder, how would the height change against time? So over here, because the cylinder has a fixed cross-sectional area, right? So the height is actually going to increase steadily, constantly. Okay, the height is going, the water is going to fill in constantly, the height is going to fill up constantly. So we're going to get a constant gradient graph because of the constant rate. Okay, so let's take a look over here. Right, so because of the constant rate, right, constant rate, right, the graph that we're looking at is a graph with a constant gradient. Okay, so what is a graph with a constant gradient? It is actually a straight line graph. We start with an empty glass, so over here it starts with 0, 0, and we're going to draw just a straight line up to represent the water over here. So actually the height, right, the height of the water, or the depth of the water, okay, height of water, right, increases constantly, increases at a constant rate. Okay, so do you see how this feels? Right, the gradient is constant, so the rate is actually constant. Gradient, rate, gradient, rate. Constant gradient, constant rate. Okay, next one. If the container is a cone, sketch the graph of H against T. So if you observe the cone, now, by common sense, the narrower part will fill in faster, the wider part will fill in slower. So over here at the bottom, it is actually narrower, right? So means that this one will fill in faster, right? The water will fill in faster over here. And at the top, it is actually wider, alright? So actually the water will fill in slower, okay? So what does this mean? This means over here, the gradient, right, will be higher because the rate is faster. On top, the gradient is going to be slower because the rate is lower. So how do we draw the graph? Let's visualize the tangents first. So something with a high gradient means it's something very steep, and something with a low gradient means something that is not so steep, like that. So actually the graph will look something like this. It will look something like this, right? Like this being the tangent of the graph. So means that the graph we are sketching will look something like this. Okay? And as you can see, the tangents over here, right? The tangents over here, right? The tangents from a steeper tangent to a less steep tangent over there, right? So over here, let me just draw in. You don't have to include this, but I'll just include here to explain to you again. Oh no. Alright, you don't have to copy this here, but I'm just including these two lines to explain to you again on what this means. So over here, the tangent is going to be steeper because it has a higher gradient, right? And over here, the gradient is lower, so it's going to be less steep, right? And because of this, the graph will look like this. Okay, so this is what we mean by the depth graph. Okay, so now this is just another example. Let's take a look at other wacky examples. Right, so over here, sketch the graph of H against T. Okay, so over here, right, over here this is narrower, right, but this is going to be a constant rate because the width is the same, right? Constant rate, the width goes the same. Alright, then over here this would be narrower, right? Over here is going to be narrow, so this means that it's going to be faster, right? It's going to fill up faster. And on the top over here, okay, and at the top over here, this is actually wider, right? And because it is wider, it's going to fill in slower. Okay, so imagine, yeah, so at first you have something like a constant rate, it means you have a straight line through. Okay, you have a straight line through like that. Okay, until this point over here. Okay, let us draw the height. Let's peg the height to the cylinder already. Okay, and because of this, over here you have a high gradient, over here you have a low gradient. So it means that your graph is going to be like this. It's going to curving this way, right? Steep, not so steep. Okay, so do you see this? Steep and not so steep. Faster, slower. Okay, so this is the graph that we are looking at. Alright, so let me draw in just in case. Yeah, okay, next one. Sketch the graph of h against t, the next one over here. So let's pack the heights first. Okay, over here is going to be wider, so this means it's going to fill up slower, so means the gradient is going to be low. Okay, so the gradient is going to be lower, it's going to be less steep over here. Okay, so this is narrow, so means it's going to fill up faster. Okay, so over here the gradient is going to be higher, means it's going to be steeper. Okay, and along this part over here, because the width is the same, okay, because the width is the same, so this will fill in at the constant rate, right? Or at least the gradient is constant, means you get a straight line over there. Okay, so let's put everything into the graph over here. So we have something which is less steep, okay, and to something that is steeper, like this. Less steep to something steeper. Okay, and we're going to continue the graph until it is filled with a constant straight line graph. Okay, means it will look something like that, straight line. Okay, if you don't want to make it so obvious, it's also fine. We can also stretch it a bit more so that it is not so you can do something like this, right? And then I'm just going to draw a straight line up like that. Okay, so let me move this over then. Okay, so mean something like that. Alright, like that. Alright, it's going to fill here, so I'm just going to stop here. Okay, so that is what we have for this graph. Okay, so I'm going to leave the rest to you. Right, you can try the rest, you can try all other wacky shapes, and I will post this solution up so that you can see what's going on. So on your own time, you should be completing this worksheet. Okay, and I will see so hopefully you get this concept, and you'll be able to use this concept to really see what's going on with this part. Alright, where we go faster and slower. Faster meaning you get a steeper gradient, higher gradient. Slower means you get a less steep gradient over there. Okay, so let's take a look at question 4. So question 4 over here, we see two containers A and B are shown below. So container A is a cube while container B is made up of two cuboids of different sizes. So initially both of them are empty. It takes 50 seconds to fill each of them up and with water flowing from a tap at a constant rate. So both of these, the tap is actually flowing at a constant rate, but the height will be a bit different, right? The change of height will be a bit different. So the graph shows, so we need to draw the graph to show that how does the depth of water changes with respect to time. Alright, so sketch the graph that shows the depth of water in container B against time. So over here, let's take a look at these two over here. Now let's take a look at A. Now A, the base area, right, is actually, if you look at A, is actually a cube. So actually it will fill up quite uniformly, correct? So it means that we're expecting a constant rate. So let us find the rate of which the volume is filled by A. So let us remind ourselves that, you know, rate, the formula for rate is equals to amount, right? Whatever amount that we have divided by the time it takes to complete that certain amount. Okay, so for instance over here, let us apply now the rate for A, right? The volume that we need to fill in is actually 20 cube, right? 20 cube over here, right? And then we need to fill in, it takes 50 seconds to fill in, so the time taken, okay, 20 cm cube. and the time taken over here is going to be 50 seconds, right? So a very quick calculation will tell us that roughly it's going to be 160 cm cube per second. So this is going to be the rate that A is going to fill up. Okay, now whereas for B over here, we can actually cut B into two parts, right? So let me draw this line over here to show that, you know, actually we can cut this into two parts, right? So the first part is actually below, right? The big rectangle below. Let us find the rate that we need to calculate over here below, right? So the rate for B is equals to the volume of water filled divided by, or actually like, okay, let me think for a bit. It's gonna be, okay, let's find the volume over here for part B. Okay, so since we don't have the specific time for that, let's take a look at the volume over here. So the volume at the bottom is going to be equals to 8 times 26 times 20, right? So this is going to be equals to 4160 cm cube. Okay. Oh, by the way, this one over here, right? This one over here is 8000 cm cube. Okay. 8000 cm cube because yeah, 20 cube is 8000. Alright, okay, and then the one above, let's calculate the volume above. The volume above is going to be 12 cm times 16 times 20, right? Just find the dimensions. It's going to give us 3840 cm cube. Okay, so we are okay. Let's move for a bit some time. Okay, so over here, right, let us take a look at some adjustments for the timing. So let's see how long does it fill the bottom. Okay, so over on the left, every second is going to fill 160 cm cube. Okay, so 1 second, wait, sorry, right? So 160 cm cube for every 1 second. So this means 4160 is going to take how long? Right, by some calculation, you will actually see that it's going to take 26 seconds below. Okay, now we can do the same above. Okay, same thing on the left, right? 160 cm cube is going to give us 1 second. Okay, and wait, hold on. Okay, so we also need to verify that both of these are of the same volume. Okay, both of these are actually the same volume. If you add these two volumes together, right, they should be the same volume, and this is why they can be filled in at the same time. They will fill to the top at the same time. Okay, so let's take a look over here. Okay, so 160 cm cube is equal to 1 seconds. So here we have 3840 cm cube. Now let's do a bit of math. You should take out a calculator and you should find that this 24 seconds. Okay, so over here, right, this one that's being plotted here, they say that the graph shows how the depth of water in container A, right? So this is actually the graph for A. Okay, so this one over here again is the graph for A. Okay, so let's try to find the height that we're going to fill first. So we're going to fill 8 cm, right? We're going to fill 8 cm over here. So let us find the 8 cm in our graph. So roughly sketching, right, will be somewhere over here, right? 8 cm. Okay, and over here 8 cm, the bottom part is going to take us 26 seconds. So 8 cm would actually fall to 26 seconds somewhere over there. Alright, so let me draw a line over here to 26 seconds. Oh wait, or more like, let me try to find the 26 seconds and move up. Okay, and try to get the line over here. Okay, so over then I can actually draw a straight line from the origin to this part, like that. Okay, alright, okay, well, this is okay, alright, so first part done. Okay, second part over here is that we have 3840, right? It's going to take us 24 seconds. So the remaining 24 seconds, right, means it's going to reach 50 seconds. It's going to be another constant rate also because like the width is fixed. So you'll look something like this over here for B. Okay, so once again, the one up there is for A, the one below is actually for B. Okay, and it takes 26 seconds to fill the first part, the remaining 24 seconds to fill the second part over there. Okay, and in the end of the day, both the height, right, as you can see over here, right, this is going to be 20 cm, this one total is also going to be 20 cm. Okay, so now the gist of the story is this. We actually can use to find the rate. Okay, we can use this to find the rate of it filling. Okay, and since this is a cube, right, the rate is pretty much standard. Okay, and then over here we can make use of this rate to determine how fast does the other parts fill in. And before we conclude, we also need to double check that both these volumes are actually the same, right? We can take this volume plus this volume over here to get this volume. Alright, and double check that the volume are the same, because if the water is flowing at the constant rate, right, at the same time you get to fill the same amount of volume, right? So this is the end of question 4. Okay, and the graph will look something like this over here, where B fills in slower initially and then it picks up at the second half. Okay, so let's take a look at question 5. So question 5, right, each container shown has a height of 40 cm. The other dimensions are as shown. So they didn't give us the width actually, but okay, they show us the same height. The containers are being filled to the brim with water which flows into each other at the same constant rate. It takes 12 minutes to fill each container. So means because the water flows in the same rate, okay, and because it takes 12 minutes to fill each container, right, means that they should have the same volume, right? They should have the same volume. So because of the same volume, they will fill in at the same time, alright? It takes 12 minutes to fill each container. Now for this one over here, right, because we don't have information of the width, so we can actually assume something, right? So since, right, both of these containers have the same width, we can just look at the cross, not the cross in we just look at the frontal area will do, right? The front area will do. Okay, because they have the same width, we don't need to look at the cross section, we just look at the front part. Oh wait, actually this is actually a cross sectional area. The one facing us, right, is actually our cross sectional area. Right, so cross sectional area. Okay, so let's take a look at this area for container A. So how do we find the area for container A? Cross section area is a triangle, so it's going to take us half times base times height. Right, so over here we need to fill in the area of 1200 cm square, right? It's going to be cm square. Okay, so the rate in which the area is being filled, right? So here we're just looking at the amount over time. So the amount is going to fill in this amount of area divided by 12 minutes, right? So each minute is going to take us 100 cm square. So 100 cm square per minute. So let's take a look at the other one over there. Okay, let's take a look at the other one over there. So over here we can split these to two sections again. Right, we can split these to two sections again. The one at the bottom and the one on top. So let's calculate the area at the bottom. Right, so the area at the bottom over here is going to be this frontal area here. Right, this front area, this one over here. Right, this area here is going to take us 20 times 50. So this one will give us 1000 cm square. Right, so this one, how long will it fill? So let's make use of this information over here. So 1 minute, right, 1 minute is going to give us 100 cm square. Wait, sorry. Okay, sorry, the other way around. 100 cm square can be filled in 1 minute. So over here we have 1000 cm square, and this bottom part will take us 10 minutes. Okay, can Alright, then the one on top over there, Now the area over here is going to be this area, right? This is the area that we're looking for. So this area is going to be equals to 10 times 20, right? 10 times 20. So this is going to be 200 cm squared. So because the width is the same, right? So actually you can also say that the area, the cross-sectional area for both container A and container B are the same. So this area over here, right, this area over here is going to be the same as this area over here. Okay, and we can use this to form certain calculations. Okay, alright, so also borrowing the same part over there, 100 cm square is going to be filled in 1 minute, right? So over here we have 200 cm square, so it's going to fill in 2 minutes. Okay, so actually what rate are we calculating? We're actually not calculating the exact rate of A though. We are only calculating the average rate of A, right? So then we can use this average rate to actually determine this part over here. Okay, alright, so let's take a look at the answer space over there. Alright, so 12 minutes, right, we're going to fill in this whole block. Right, for 12 minutes we're going to fill in this whole block. So let me draw this ending point over here. Alright, and we also have another info. So let us draw the straight one first, this one over here, which is the easiest to draw. So we have to fill in the first 10 minutes and then we fill in the top in 2 minutes. So in 10 minutes, right, we're going to fill in 10 minutes we're going to fill in 20 cm, right? So let 20 cm height. So over here let me draw somewhere halfway, right? And let me pinpoint at the 10 cm, a 10 minute mark. Okay, so this one like this, somewhere like this. Come on. Okay, somewhere like this. Okay, so this is going to be 20 cm high, and because it is a rectangle, right, so it's going to have a constant rate over here, right? So let me adjust the axis. Alright, okay. Next, the next part is going to fill into the top, so I just need to draw another straight line to the top. Okay, so just like that. Okay, so this one over here is going to be our container B. Okay, so what about container A? Now container A, right, is going to fill in much faster over here. So this part is actually narrow, so the gradient is actually higher, right? And the one on top, because it is wider, the gradient is going to be lower, right? So the bottom is going to be steep, the top is going to be less steep. So your graph will be from a steep graph to a not so steep graph, like that. Okay. Let me just draw this so that I can get my curve out. Right, so this is nice curve. So roughly like this. Okay, so this will be my container A. Okay, so don't worry too much about this one. I think it's just to give you a context of, you know, some calculation to determine some filling up rates, and based on this, right, we actually can draw this graph over here. So once again, the main idea for this part of the chapter is steep gradient, a steep tangent, higher gradient, higher rate. Not so steep tangent, less gradient, less rate. Okay, fill in slower. Okay, so this is what we mean by converting, right, making sense of the gradient to tell us how fast or how slow something is. Okay, so that's all for this chapter, for this subtopic. Make sure you go back to the front few pages to finish drawing the graph. The solutions will be posted on Google Classroom for you to view. So that's all that we have today. Hope you have a great time and see you soon in the next video.